Hi, good morning, everybody. Here we are. It is a pleasure to introduce our first plenary speaker in this edition of SEIO 2022, Professor Alan Gelfand. He is currently Emeritus Professor in the Department of Statistical Science at Duke University. He has a strong and fruitful scientific trajectory. Particularly, he was working as visiting professor at prestigious universities like Harvard, Sydney, Nottingham, Washington, among others. He has been elected member of the American Statistical Association, the International Statistical Institute, the Connecticut Academy of Arts and Science, the Institute for Mathematical Statistics, and the International Society for Bayesian Analysis. Indeed, he was the former president. Okay. He has been awarded with the American Statistical Association Distinguished Research Medal in the Statistics and Environmental section. He has also been recognized with other awards like the Parsons Prize by his very extensive research career with very relevant contributions in the field of spatial and environmental statistics, hierarchical model, Bayesian statistics, with more than 300 publications in this research area, and being the supervisor of more than 13 doctoral theses. He was recognized as one of the 10 most cited mathematicians in the world in the period 1991-2001. Another important feature of his CV I would like to highlight is his impressive editorial work in the most prestigious journals in the statistical research area, including, among others, Journal of American Statistical Association, Bernoulli, Journal of Multivariate Analysis, Spatial Statistics, and, as we know, he is currently member of the editorial board of a Spanish Statistical and Operation Research Journal, TEST. Indeed, we will need plenty of time to describe in detail his vast research production and activities, but people is now waiting for your interesting talk. So this is your time for presenting the talk entitled Long-Term Spatial Modeling for Exploring Incident of Extreme Heat Events. Whenever you want. Thank you a lot.
¿Cómo puedo? ¿Puedes oírme? Sí. Muy bien, Lola, muchas gracias para las palabras amables y un placer asistir a este SEO 2022 y placer visitar a Granada, una ciudad muy encantadora, está claro. Es un honor para haber escogido yo para presentar la primera conferencia. Vivo muchas semanas en España, en Zaragoza, y puedo conversar en español muy social, entiendo mucho, con poca interpelación, y leo y veo películas y tele, pero no puedo presentar toda una hora en español. Y ahora cambio a inglés y lo siento, perdóname. Okay, well, that sounds different, doesn't it? I have 3 stories to tell you today, and it all involves a team that I've been working with for a while now, mostly in Zaragoza, but a few other places. Some of the names are familiar. Some of the people in the audience are here from the group. And again, it's just a pleasure to be here. This is what do we say, another day in paradise? It's a pleasure. So let me talk to you a little bit about extreme heat events. That's what we've been working on, and the 3 projects that I'm going to summarize are in papers in Royal Society A, and then there's one in SERA, and there's one forthcoming in the Annals of Applied Statistics. So the work moves on, and as I said, we seem to be doing pretty well as a team. The issue that we're dealing with is, I don't think I have to ask you to appreciate the fact that we are dealing with, climate change and global warming. But the interesting question is, in some sense, we're not so good at quantifying it. I mean, you see, the usual pictures, and those are not at the level that, we as modelers, as statisticians would like to describe things. And so the challenge is people talk about heat waves all the time, but they're not really very formally defined in the literature. In fact, I'll show you what the definition is in just a second. But it turns out that we can look at extreme heat events in terms of exceedance of a local threshold, and that gives us a definition that we can actually work with in terms of probabilistic specification. And so as a result, an extreme heat event is going to be defined as a run of consecutive days above some specified local threshold. And in particular, these are the characteristics of an extreme heat event that we'd like to be able to say something about. In other words, basically, how often, how long, how severe, things like that, we'd like to be able to say something about, quantify them a little bit more. So we're going to, as I said, tell 3 stories here. And the first is we're going to build a fairly sophisticated space-time threshold exceedance model to capture all these characteristics. Then we're going to develop a way to capture an extent of an extreme heat event, essentially as a spatial surface over a region, the proportion of that surface that is exceeding its local threshold. And then we're going to go to quantile regression, because quantile regression enables us to look at high levels rather than just mean regressions, which are not interesting enough for extreme heat. And we will therefore talk about conditional quantiles, which enable us to talk about persistence, but we'll also show how to convert to marginal quantiles to enable spatial interpolation, which again is important because we do not monitor everywhere that we need to learn about. So basically, spatio and temporal stories are what we're going to play with. Again, this is just some words that describe the, what we all already in the audience already know. Maybe the last bullet is worth a word or two, because it's a combination of health outcomes, economic outcomes that we would worry about. And in this situation, extreme heat can definitely be problematic. And that's why we need to know how long it's going on, where it's going on, how extreme it is. And so we need to understand this phenomenon a little bit better. Okay, so here's the problem with the heat wave. You can read that definition. I'm not going to read it to you. But you can see that it's more qualitative. It's not really quantitative, right? It doesn't tell you what unusual means, or how long, or what region, or it's a little vague. Whereas, as I said at the outset, the concept of an extreme heat event is straightforward, and it's just based on an exceedance of threshold approach. And this is going to suggest that we should be playing with the analysis of extremes, and I'm going to argue that we don't. But I'll explain that as we get to it. But again, the idea will be that a local extreme, say, could be the 95th percentile of local temperature series during, say, warm months. Okay? So here's the story about why we're not going to go down the extreme value sort of pathway. It actually is not going to give us the features that we need. It's not going to talk about duration or average exceedance or maximum exceedance. What we really are looking at is the occurrence of events in the form of a time series over a window of time. And so what we really need is a model for daily time series, and that's what I'm going to show you in just a couple of slides. And so, in fact, what we really need is a joint model at different locations with spatial dependence. And in fact, what we need is a model that's non-stationary, because of the fact that there's evidence of change over time. And so that's where we're going to go with this. So let me tell you a little bit about the first contribution. Again, a space-time model based on daily maximum temperatures. And the first thing to notice is the second bullet here, which says if I just built a fairly sophisticated time series model, autoregressive time series model, it's not quite going to work well enough. And the reason it's not going to work well enough is because it'll be driven where most of the data is observed, and it will fit poorly in the upper tails, and the upper tails are what we care about. So therefore, a regular autoregressive model is not going to be good enough, and so we're going to have a switching model, a threshold switching model that switches between observed states, one defining an extreme heat day above the threshold, the other defining a non-extreme heat day below the threshold. And then we'll introduce spatial dependence and transition probabilities, and so you can see that there's some sort of maybe familiar Markov switching model. So that's where we're going with this. All right, again, wouldn't surprise you that we build a hierarchical model, we fit it in a Bayesian framework, we use Markov chain Monte Carlo. At the end of the day, the model is complicated, but the fitting is fairly vanilla, and so we don't need to necessarily get very sophisticated with the model fitting. It can be slow, but it's as I said, fairly straightforward. And then what we're going to have to do is generate lots of posterior predictive time series, because those predictive time series are going to enable us to really see what's going on behaviorally in terms of these features that we're interested in. They'll also enable us to develop these extents that I'll get to in the second part of the talk. Okay? So again, this is just repeating some of what I've said earlier. This prediction is really critical for human health issues, ecosystem and economy issues, and the ideas, again, some of the things with fully model-based inference will certainly enable us to predict at unobserved locations. That's the usual Bayesian interpolation or Kriging, not necessarily Bayesian, but interpolation Kriging anyway, and we can even deal with missing information in the time series. So again, this sort of imputation business, I think, is well known for almost everybody in the room. I think this slide is useful only in the sense of trying to clarify what we usually think of as the distinction between weather and climate. In other words, climate is what you predict, weather is what you get. And in particular, that's the situation we're looking at here. If the goal is to predict, just an annual time series of daily max temperatures, the regular autoregressive model will be fine, because it's just a random, as I said, realization of weather. But if you're really interested in climate, these features of climate we've been talking about, say over a decadal period, then our two-stage model consequentially outperforms a simple autoregressive model. So that's where we're going with this. All right, the data we're interested in comes from the Comunidad de Aragon, and I don't have to tell everybody here exactly where that is. And in fact, the features of it, some of the features are written here. So it has a substantial elevation range, and it also has several sub-areas of climate that are interesting to look at and will, for example, enable us to look at, say, two subsets for comparisons. We have 18 sites over quite a long period of time there, as you can see, 62 years. The first decade is used to obtain location-specific thresholds. It doesn't really matter. I mean, you could use some other window to get these thresholds, but we just took the first window as a place to benchmark. And we focused on, again, June, July, and August, since these are the period of extreme heat events. I just wanted to comment that one of the challenges for us is having only 18 sites over all of Aragon. Clearly, spatially, we're not in the situation that I'd like to be. I'd like 40, 50, 60 stations, but we don't have them for the duration that we would like, and so we're depending a lot on faith here, and whether you're a believer in faith is a different issue, but all I'm saying here is we do the best we can with the 18 stations that we've got. Okay, let me show you some quick pictures here. So again, probably everybody knows something about Aragon, although maybe not all of these smaller villages. I certainly have learned a bit that I did not know before spending time in Zaragoza. And so here is, for example, altitude versus threshold, and not surprisingly, you can see the kind of inverse relationship, and it's actually fairly linear between the percentiles and the altitudes. Here you can see the temperature picture for 76 to 85 on the left, and 2006 to 2015 on the right. And I guess the bottom one is the difference between those two pictures. And what you can see is, particularly earlier in the season, there's a substantial difference in daily max temperature. And then as we move closer to September, all of a sudden, the difference starts to move in the other direction. So it seems, in a sense, that the warmer weather is coming earlier and, in fact, substantially different in, say, April and May compared with what it was 40 years before. Okay, and I'm going to demonstrate that a little more inferentially. This is obviously just descriptive, but I will show you a little more in a moment. So if we now have this definition of an extreme heat event, then here's another way to look at it. You can look at this window versus this window and compare the incidence. And of course, it's not perfect, but I think just scanning it, you'll clearly see that the incidence is much greater in the later decade than in the earlier. And so I think that, again, suggests a reason for looking at this. And if we look at an extreme heat event, which is now some sort of not just individual days, but consecutive days, once again, we see the pattern of generally much more extreme heat in the latter decade compared to the earlier decade. Okay, so this is the evidence that is really going to motivate our temporal comparisons, and the spatial story, I guess, is expected as well. We do need to worry about variability. Homogeneity of variance is never going to be sensible here. We expect spatially varying variances, but we also worry about above threshold and below threshold variances. Again, below threshold, there's a lot of space to work with. Above threshold, not so much, so the variances cannot possibly be the same. So we will have above and below threshold variances that are spatially varying. Okay, so let me get into a little bit of the detail of this model, and then we'll move on, as I said, to some of the other contributions. But let's say a little bit about this for a while. So let's just let YTS be the daily maximum temperature at time t at location S. And again, a two-state model. So we're going to have this binary variable, UTS, which denotes the state at time t for location S. All right, and so UTS is not what I would call a latent variable. It's true that we don't observe it everywhere. We only observe it at the sites we're at the days we're looking at. But it is essentially a state variable, and I would not call this, for example, latent state, I would not call this a hidden Markov model. It's nothing quite like that. The UTSs are again, available where we observe the data. Okay? And so, again, we're interested in, again, extreme heat events relative to the local thresholds. UTS then is a spatial binary time series process. Provides a time series, again, reflecting the times of transitions. Again, if you give me the actual daily max temperature at that day, at that location, you immediately know UTS. In fact, we're going to look at it in the opposite direction, of course, to model UTS. Okay, so this allows transition probabilities, ensures things are local. Again, the idea is that it makes sense to think about transition as depending upon the previous day's temperature. And these bullets here are trying to just explain that, but I think verbally it's obvious. If the previous day was in extreme heat, that should give you obviously more chance of staying in extreme heat. If the previous day was not in extreme heat, then you'd have less of a chance of moving to extreme heat, and that's all the words are trying to say. And so again, I've used the word persistence before, but we're trying to characterize persistence of extreme heat, consecutive days of extreme heat. Okay? So the model looks something like this. Obviously, this is a very abbreviated version of it, but that's sort of what's going on in terms of the structure. And so it requires 3 model specifications. YTS given we're below threshold, YTS given we're above threshold, and the switching, the binary process. And again, everything's conditioned on the previous day's observation. Okay? By the way, you could ask if we could look at autoregressive order 2, autoregressive order 3. We've done that, and actually, in terms of the inference, it doesn't really bias anything, so everything I'm going to present is just lag 1 autoregression. Okay? So in terms of modeling YTS, when UTS is 0, it seems natural maybe to try to play with the truncated normal distribution up to the threshold. And so we do something that sort of looks like this, where I'll tell you what U0 looks like in just a second. But something like this seems to make sense when UTS is 0. When UTS is 1, we think life could be a little different here. And the reason is when we're looking at upper tail behavior, it's natural to want to incorporate what they call upper extreme dependence. There's an extremal tail coefficient that can be introduced, and the idea of multivariate tail dependence seems to be natural in terms of the temporal story that we're looking at here. And so the multivariate normal is not going to be good enough because it has tail independence, but the multivariate T family does exhibit tail dependence. So everything here is done with truncated T distributions on the support above the local threshold. Okay, again, it may be a minor technical issue, but in fact, it does not affect the results much, but in the interest of probably getting a little better approximation to the process, we use the truncated T's. Okay, so here's the model for the mu TS's. UTS again here is either 0 or 1. And so you can see we've got an overall intercept, a spatially varying intercept, and then we've got contributions for yearly contributions, elevation, latitude, and then some sort of seasonality contribution. All the things you'd expect in a model that looks like this. And again, even though it starts to look ugly, remember all of this is linear, and so in terms of model behavior, this is really not going to be badly behaved. So this just reminds you of what each of these terms are, and the only other thing I didn't mention was that row here, where is the row? I've got to go back one. The row here is, there's a different row above than there is below. You might ask for a spatially varying row. Not here. We played with it. It seemed to be pretty hard to identify, pretty hard to say much about, but we have played with it in the last example that I will show you. So if you can be patient, we'll get to something like that. Okay, so again, this is just describing the terms. I have to model the binary switching process, and for that, we just used a probit link, and again, the same kind of modeling structure that we had for the local mu's. Okay, and again, spatially varying intercept, I think, is critical here. Okay? So let me just clarify a little bit. The competitor, or the straw person, whatever you want to call it, would be just the autoregressive model without this state switching. And so in that situation, that's what we're going to try to improve upon. And so if I do model comparison, that's what you're going to see. So we'll do, because there's only 18 sites here, it's actually easy to do single point deletion, leave one out validation. And so in particular, I'll just show you the results. We've done all 18, of course, but I'll just show you 3 of them. And we'll deal with model comparison through prediction of exceedance days. In other words, we're going to look at the prediction of UTS, which is again, that binary variable that indicates exceedance or not. And I guess there are 2 possible errors. You can predict UTS as 1 when we observe 0. You can predict 0 when we observe 1. Obviously, the second error is more important because it's failing to predict an extreme heat event when it happened is more problematic, since we understand that we're worried about the impact of these extreme heat events. Okay? Again, we can go beyond our 18 sites using customary kriging, and I'll say more about that in a bit. But we have, again, then these conditional errors. We have a conditional error for saying it's 0 when, in fact, the previous day was an exceedance, so that would be a mistake. And the other one turns this around, saying it wasn't when, in fact, it was, when in fact it wasn't. And we can marginalize over these to get kind of a simpler version. So let me just show you a quick picture of the error rates here. And so these are the error rates. And the takeaway from this, without obviously there's too much to stare at, but the point really is that the base model has much higher error rates. The base model has much higher error rates everywhere you look. We're doing worse with the base model. So in some sense, this is supportive of the model comparison to select our model. Here's another way to quantify it, the base model versus our model, looking at, say, 1-day lag, 2-day lag, or even 3-day lag. We can look at the incidence of these conditional errors. And you might look at this and be slightly horrified because these errors look pretty large, and you would have thought with a decent model we should do better than that. And so the story there is that the error rates are large because exceedance days are not common. When they occur, they usually occur in short duration, and so failure to predict them is not compared to, say, just a coin flip. A coin flip might do better in some days, but it's going to do horribly through the window outside of June, July, and August. And so I think that's why these numbers look the way they look. And originally we were concerned about them as well, but if you, again, put them in the appropriate perspective, I think it's okay. As far as model adequacy is concerned, there are too many words here, so maybe we'll just look at significance. The intercepts, elevation is significant, latitude is insignificant, the autoregressive coefficient is really strong in both cases. And if you look at the random effects, I think this is a slightly interesting story. Let me just give you a word or two here. If you look at the random effects for the above threshold process, there doesn't seem to be any trend. If you look at the random effects over time for the below threshold process, the trend is clearly substantial. So what is that saying? What that's saying is, yes, it's getting warmer, but the upper extremes are not getting larger. In other words, yeah, overall, if you put this together, you're getting warmer weather, but it's not manifested in terms of more extreme exceedances. Okay? Let's go to the second contribution, since I'm not going to have that much time, and I'm sure everybody will want coffee fairly desperately. And so let me move along. Okay, so we decided that the extent of an extreme heat event would be interesting spatially. And so what it is kind of a block average of indicator functions. There's an indicator at every single location in some region, and you're looking at the proportion of those indicators that are 1, the proportion of indicators where the threshold was exceeded. And so, again, we're going to examine this over the same set of data that we've got. We can calculate it daily, we can go seasonal, we can go decadal. I'll show you this in just a few slides. And as a result, we can even extend it to persistence and make comparison across decades. And so this will bring out, again, a different way of seeing the, in a quantitative way, the impact of climate change, of global warming. So again, risk assessment in this context has been discussed a little bit. There's even some notion of what we call excursion sets that's been talked about. And so there's a little bit on this, but none of it's quite like what we're doing, and none of it formalizes the notion of extreme heat event explicitly as a stochastic object. In other words, some of it, a lot of it is primarily descriptive, and that which is mathematical or more probabilistic is not quite what we're doing. And so just read the very bottom here. That's the most important thing on this slide. And it's, again, just the proportion of the area of the region whose daily maximum temperature for the day is above the associated threshold surface. Okay, it's like you can imagine there's a light bulb at every single location in the region, the sub-region, and what proportion of the light bulbs are turned on. That's essentially what we're looking at. Okay, so what we're looking at is an extension of what's called the spatial cumulative distribution function. That arises as a stochastic integral over a realization of a stochastic process. So that immediately tells you that it's going to be a bit of a challenge to work with. It's a conceptual random object. It can never be observed, and it can never be calculated in closed form. Does that mean we give up? Of course not. What it really means is we'll have to use maybe Monte Carlo approximation to get approximate realizations, and we can play with it analytically in the sense of getting moment properties, and we have got moment properties for our extents, but in the interest of time, I'm not going to describe some of that analytical calculation. But an important thing to think about is that this is a post-model fitting activity. We're going to be able to fit the model, store the output from the model, and then use the output from the model in order to study extents. So you fit the model, whatever model you're interested in. It doesn't have to be the model that I just showed you. It could be any model that you're interested in. You can fit the model and save the output, and then after that, you can choose any regions you want, any days you want, any windows in time you want, and you can use, again, the model output to assess extents. So in some sense, that's attractive. So here's what it actually is. Take a look at this for a second. This is the object. This is the spatial CDF. I'll get to our object in just a second. This is spatial CDF, and again, it's a proportion of the realization of D that lies below W. So this is the formal definition. You can see that because this is a random realization of a process, the indicators are a random binary process, and this is therefore a random variable, but it's an integral that could never be, as I said, calculated exactly. And again, people call it a CDF because it behaves like a CDF in the sense that as W goes to infinity, the whole surface will be less than this, and you'll get 1. As W goes to minus infinity, none of the surface will be above, and this goes to 0. So it's non-decreasing. So you can see why you might think of this as a CDF, but it's a different kind of CDF. It's nothing to do with the marginal CDF associated with a random variable at any location. That's something that looks like this, and this is a constant. Again, given parameters, it would be viewed as a constant. Okay, and again, I gave you the story about stochastic integrals a minute ago. So here's our spatial extent, which we are actually going to work with. So we're going to look at the incidence of YTS minus QS, the local threshold, being bigger than some W. Probably W equals 0 is what we're most interested in. In other words, that's really an exceedance, but you could play with other W's, maybe at least 1 degree above the threshold, or maybe at least 1 degree from 1 degree below the threshold, and so we might as well allow W to be flexible in there, and we've just investigated how extent can vary as we vary W. For the same price, we might as well explore that. As I said, we can calculate mean and variance, but I'm not going to go through the details. As I said earlier, it's the block average of indicator functions. You can see that as well. And here is then the object we're going to actually work with is this Monte Carlo approximation to that. You might ask how well that Monte Carlo integration will work. And that in itself is an interesting question. In other words, when you start dealing with stochastic integrals, sort of Ito integrals, then you can run into issues about whether the discretization will actually converge. And in some cases, it's well known, and sort of depends upon the quadratic variation that's associated with the integral. And so I'm not going to get into that, but in this situation, we are essentially safe. And so if we work with a fairly dense grid of locations within our region, our approximation should be pretty close to what the truth actually is. Okay? And so that's just what I'm saying over here. Okay? So how are we going to do something like this? How are we going to do something like this? Well, what we need to do is pick a set of locations that we're going to work with here. So that's going to be some sort of grid. and then we need to get indicator functions. But if we take any particular realization, of the process, that'll give us a realization of the extent. But if we want to see the distribution of the extent, then we need to generate lots and lots of realizations. So it turns out that we need to generate many, many posterior predictive time series in order to get the posterior predictive distribution for this. Again, none of this is hard, but computationally it can turn out to be quite a bit. In fact, I'll show you that in the next slide, but just a couple of quick remarks here. We need to create the local thresholds, and the simple way to do this is just through kriging with elevations, and so that's what we did to fill in the M's that we need. This is interesting to mention. You could think about an empirical extent. In other words, who needs the modeling? Why don't you just look at where the stations you observed and look at what proportion of the observed stations exceeded the threshold on that day for the region you're interested in. And the problem is with 18 stations, we don't have enough. You could go to some set, and you might find 3 or 4 stations that are in that set, and so the possible values for the extent are 0/4, 1/4, 2/4. It's not good enough. So we really need the gridding. We really need this, and so typically we've been using M on the order of 6,000 to 8,000 to get much smoother extents, and then, as I said, replication in order to see the distribution. All right, so that's the daily extent, and in the data that I'm about to show you, we're actually going to have 2 indexes for time. One is the day within year, and then one is the year, and so this is there for the extent for day L within year T, and then we can start to average. We can average over any window of days, any window of years, and we can start to create average extents. And in particular, we've been playing with decadal averages and summer season averages, so 10 and 92 are the numbers for those. Okay? We also, because persistence is important for us, we decided that we could even consider extents for 2 consecutive days, and so that's what the 2 here means, and that means the indicator for day T and for day L and day L plus 1 in year T both exceeded. And so you can get to R persistence and have things that look like this. Again, it's just Monte Carlo integrations, and so all this is a tool that will enable us to understand more about the extent of heat for a single day and the persistence of heat. And so again, we go back to our particular data set, and we look at 2 subregions. One is the Pyrenees, a region we carved out in the Pyrenees. Another is a region in the Central Ebro. The region is a little bit smaller in the north. 1 kilometer by 1 kilometer grid cells, 7,800. 2 kilometer by 2 kilometer in B2, a larger region, almost 6,000. 5 decades. Here's where the numbers do start to climb. 50 years by 92 days, by 7,881 grid points, by 500 replicates, about order 10 to the 10th points. So it's not that this is complicated, it's just that it's a lot of data to move around, and particularly will exceed, for example, what you can ever plug into R, and so you have to find clever ways of doing this, and fortunately my team is clever, and so they're able to do these things. So let's just look at a couple of features of this. If we want to look at the evolution of extent over time, so this kind of shows you for the 2 regions the story that I'm trying to tell. Extent of single day is definitely increasing over time, and even extent of 2 days increasing over time. Extents are not large. In other words, maybe we're going from 7.07 to maybe about 0.11, so the numbers are small. We're not seeing extents of 50, 60%. They're not that big, but there's evidence that they're increasing, and I guess that's all we're trying to demonstrate here. If we look at decadal averages, another way of trying to capture this, then again, we can more or less see an extent that looks like this. and something that looks like this in the Pyrenees. This is for the single day, and this is for the 2 days. So again, the numbers are small, but at least there's some quantification of the direction. Okay, here's another interesting thing that you can tease out of this, and that's the time to the beginning of extreme heat events. And one thing you can see is these are all moving down, and that simply is saying that summer is coming earlier. Summer is coming earlier. And you've probably noticed it's been hot as hell in May and June here. I've been in Spain now since the beginning of April, and it has certainly been warmer, than I remember before, and I don't have that many years here. But all I'm saying is maybe this is not a surprise, but it's something, again, that we can tease out. All right, so let me finish with my last story. It's on quantile order regression. I said at the very outset that what we're concerned with here is that the mean is not going to tell us a very good story about the upper tails that we're interested in, whereas quantiles will be more useful in that situation, particularly maybe the 0.95 quantile. And so, again, we have the same business as in the last analysis. We're going to look at 2 time scales. We're going to look at days within summer season across years. All right, and I'm going to show you a pretty ugly mixed effects autoregressive model needing 4 spatial processes. The novelty is we're working with the asymmetric Laplace distribution for the quantiles. That's a fairly natural choice of distribution to work with. It corresponds to a familiar check loss function that is often used to optimize for quantile regression. As I said, we're going to focus a little bit on the upper 0.95 quantile. The autoregressive model that we're going to specify yields conditional quantiles, as again, the conditional quantiles are useful for persistence, but the conditional quantiles cannot be Krieged. They cannot be used for spatial prediction because you need the previous day, and we don't have the previous day where we haven't collected any data. So what we do there is we go to marginal quantiles, and they enable interpolation over the region. And the cute thing that we can do is, from the conditional quantiles, we can extract the marginal quantiles under this asymmetric Laplace distribution. Turns out to be, I think, a nice little idea that I don't think has been used before. Okay, so here is a little bit of a story about quantile regression. Some of you are maybe more familiar with this than others, but there are sort of 2 approaches in the literature. One is what's called multiple quantile regression. That is, you take any quantile you want, fit a model for it. Go to another quantile, fit a model for it. Go to another quantile, fit a model for it. Each quantile gets its own quantile regression. And again, you can minimize a check loss function, or you can build a more elaborate stochastic model, which is what we're going to do. The second option is a joint QR. And so you build one model that provides all of the quantiles. In other words, if you provide the distribution for y, t, l, s at every L, every T, and every S, then you can tease out its quantiles automatically. So that seems more natural. In particular, the joint models avoid the possibility of what's called quantile crossing. You could have a quantile 0.95 that looks like this, and a quantile 0.90 that looks like this, and if they cross, doesn't seem to make sense. In some cases, the 0.9 quantile is higher than the 0.95. In other cases, it's lower, and so quantile crossing could be an issue. We have been playing with that recently, and we've got some, I think, some very pretty results to enable us to do the joint version. But what I'm going to show you now is the multiple version. That's where we started, and it's still pretty demanding. Okay? I also could make this argument on behalf of the multiple quantile modeling. Just look at this for a little bit. If you think about the quantile regression as specifying a mu tau and then an error where the error distribution has 0 as the tau quantile, so mu tau is the tau quantile for y, then if this is equal to 0, we impose a soft or stochastic order on the quantiles. If we write for a tau star something that's the same as this, but for a different tau, then we'll be able to argue that mu tau star is stochastically larger than mu tau. So it's not absolutely larger, but stochastically larger. That might be good enough for you in practice. Okay, here's the asymmetric Laplace distribution. Some will be familiar with it. The most common version probably is the double exponential, which gets used a lot. That's the one that's symmetric around 0 usually and provides a lighter tail version than a normal if you're looking at heavy tails and lighter tails for investigation. In any event, it's got 3 parameters: a location parameter, a scale parameter, and an asymmetry parameter. And it's convenient to work with because, again, it has closed form expressions for the CDF, and again, we can do things with it. But here's the real game. Here's the real game. This may not be very familiar to you, but it turns out that realizations of this asymmetric Laplace, okay, I've said mu to be 0 here just for convenience, can be captured through a realization of a normal 0, 1 variable and a realization of an exponential 1 variable. This guy has exactly that distribution marginally. In other words, conditionally, it looks like a normal, and marginally, it has exactly this distribution. So that's wonderful. Why? Because that enables us to do everything conditionally on all of the parameters, condition on everything, and work with all the usual normal theory. And the normal theory is really easy. The normal theory allows all the joint distributions and allows easy spatial development, allows all the conditioning we want. Everything is easily done working in the normal family. And so this is actually an elegant result. If you wonder how somebody came up with this, damned if I know, but all I can say is the proof is pretty simple. All you do is show that the moments agree completely. You just calculate moment by moment by moment, and all the moments line up, and then you have the standard result that says the distributions are the same. Okay, so here's the model, space-time model. Again, as I said, 2 indices, day within year, and this is the conditional quantile autoregression for YTL, day L in year T at location S, given the previous day. And we're going to write it in a form that looks something like this. And so this is the tau conditional quantile. This is the object we need. If this starts to look like some of the stuff we were doing earlier, that's because it is. And so here is sort of a version of what that might look like. But we're adding in a bunch of extra stuff here. We're adding in a spatially varying intercept. We're adding a spatially varying trend. And we're also introducing some space-time process. And even this sort of thing, this term is in here to give a yearly adjustment for the fact that some years are warmer and some years are colder, and we need maybe a temporal random effect to adjust for those. So that's what's going on. And again, you're not going to absorb all of this, although there is a quiz at the end. So hopefully you've been taking notes. Anyway, let me just show you some results from this. The results, again, they're not going to mean very much. Here are the intercepts over the quantiles. Here is the seasonality over the quantiles. Here is the coefficient for elevation, and here's the coefficient for trend. And I think the most important takeaway from this is at least 3 of these guys are not monotone necessarily. So if they're not monotone, that means we cannot insist that the quantiles just sort of be additively going up. In other words, a simple quantile regression like that would never work. And so that's one of the reasons why we need a model of the sort that we have. All right? The autoregression is really strong spatially for small tau, maybe at this magnitude, and for central taus on this order. So the random effects, again, there are 4 processes here, 4 Gaussian processes: an intercept process, a trend process, an autoregressive coefficient process, and the variance process. Again, not particularly linear, so again, we need we really need to have a model something on the order of what we've actually been building. Okay, So if we look at the conditional quantiles, this gives us some flavor for persistence. And again, there's too many pictures here, but let me just quickly tell you that the story might be told best in this one, maybe this one, and this one, where we're conditioning on a previous day which was warm, a previous day that was warm, and the persistence, you can see, is quite high. The persistence was quite high, and again, this is just a particular day. But so again, I think again you can get some sort of spatial evidence of what's going on. All right, let me just finish up with some words on marginal quantiles. The interesting point here is that it is straightforward if you again work with these asymmetric Laplace errors, use the conditional Gaussian representation to extract marginal quantiles. Okay, and in fact, once you get marginal quantiles, you can do them for a single day, Krieging. You can get marginal quantiles weekly or monthly averages, get a quantile surface over the region, get a block average to obtain all sorts of quantile summaries that spatially might be interesting. So just a quick word on this. This sort of looks again like what we've already been doing, so I'm not going to repeat everything here. When you stare at something like this, if you look at this and then you sort of stare at this, your thought might be, well, does this somehow look like a marginal quantile? And the answer is no, it's not quite. The probability YTL is to this marginally is not equal to tau, and so we need to make some sort of adjustment to this in order to make it work. And to make that adjustment is not that difficult. It turns out that if you plug in to sort of the centered model, you can work out, going back in time, that it looks something like this. And so as a result, this object here, I'll call epsilon tilde sub L, and you can actually get its distribution. And this random variable doesn't have zero as its tauth quantile, but we can find its quantile. Each of the terms in here, each of these guys here, because they're asymmetric Laplace, they have zero as their quantile, tauth quantile, but this is the sum of them does not. And but we can actually play with this. This gets a little ugly, and at this stage of the talk, not worth looking at. But we can basically do a Monte Carlo integration to calculate this over all d's, and then we can use some simple root finder to solve for what we want. So altogether, we can do this. It sounds like it would be a pain in the butt, but we can do it. And again, we can do it at new sites, and we can create services to show all sorts of pictures. The last bullet, I think, is worth noting here because this is something that we don't usually do in spatial analysis. We're interpolating a parameter, not an observation. Usually when we do spatial prediction, you're predicting new observations at unobserved locations. Here we're trying to learn about parameters at unobserved locations. So in fact, we're getting posterior distributions, not posterior predictive distributions. But we can do it. And I'm just going to show you a quick picture here of the posterior mean, again, for that same day. Again, these are for 3 different choices of quantile, 0.5, 0.5, and 0.95. And you can see some spatial behavior in the quantiles. And, again, there's more here than you're going to absorb at the moment. I'm just going to finish with what we're doing right now, which I said was this non-quantile crossing problem. We have a general characterization for non-quantile crossing for the QAR1 situation using something called the Kumara-Swamy distributions. I'd be curious if anybody in the audience has ever heard of the Kumara-Swamy distributions. Probably not. But they're sort of like beta distributions, only they're nice because they have closed form CDFs, unlike the beta distributions, which require numerical integration every time you want to evaluate them. So that really helps in terms of implementation. And so we've extended this to QARP, multivariate QAR1, spatial QAR1. It's all moving forward, and if the gods are good, the paper may be done in about a month. Anyway, thanks very much for listening.
Thank you very much, Alan. Now is the time for question, suggestion, please. Okay, José Miguel Angulo.
No funciona?
Okay. This is
Nice to see you.
nice to see you again. Yes, we met last week in Lleida. So it's well, it's very strange to be here for this question. But okay, all right. I will just. It's not a question actually. I think because the talk was so dense in some respect. I think I'm sure I have missed some points. This is why I wanted to ask you. In the beginning, well, you mentioned this two-stage Markovian approach, which is thinking of a 0-1 random field, which is similar to the intrinsic case in Kriging. Immediately one think, okay, this extreme heat event, it can be more or less important depending on the excess, of course. No? You are missing, you are conditioning to the, you are exceeding a threshold, but in some sense you discard, in a first stage, you discard the amount of excess when you take 0-1.
No.
In the beginning, I mean.
Well, don't forget there are three processes going on here. There's a Y for below, there's a Y for above,
Exactly.
and there's the indicator, as you say. So in the zero, yeah, we're in the binary process, we don't take into account the magnitude, but then the other processes do.
Yeah, I have seen that you keep this information in many ways. Then, I don't know, this is I wanted to ask because I have missed this point. You consider a non-homogeneous threshold, which is a QS, allowing for non-homogeneity along space. Then I understand the W you put in the expressions. This is something like increasing the threshold by a certain value, W. This value could be also non-homogeneous, probably, because in some sense, because the non-homogeneity comes probably from some environmental conditions, local environmental conditions, covariates, probably, then you can think of considering a family of increasing functional thresholds, say, where your W can also depend on S. I don't know if this can be something to think about.
This is a delightful question. Actually, the challenge is that we can Krieg the thresholds over the whole region, but it would be hard to tell how to Krieg the this WS spatially varying over the whole region. And it would be, I think, hard to, I think it'd be hard for the data to say much about what that should look like. And so the idea is whatever the threshold is, 1 degree higher or 1 degree lower, and not necessarily 0.6 degrees here and 1.3 degrees there. And I do think it's interesting, but I don't think the data is capable of informing about that. Thank you.
Thank you a lot. Thank you. Anybody want to ask suggestions? Yes, Lola.
I'll repeat it if people can't hear it.
Yeah.
sensible enough to fit or not? If you have a large number of locations.
Well, that would only make life better. The runtime is sort of going to be linear in the number of locations, and so that's really not going to hurt us too much. And in fact, we have pulled out some additional sites. So I think we can get to 40 or 50 additional sites, but we don't have the full window of time for all of those sites. But in terms of running the model, it's definitely not a problem. So again, I just think that would make us more comfortable with interpolations. In fact, I think we've actually used some of the holdout sites that we were able to get otherwise to do some validation of the model for the 18 sites that we did work with. And so I think the question is fair, and as you're pointing out, I think we would generally be uncomfortable working with so few, monitoring sites over a fairly large region. Mi culpa.
Thank you. Nice talk, anyway.
Thank you, Lola. Good. Some questions, suggestions? Okay, this is very nice talk. One only puntualization because it's the time for coffee, but for example, in terms of heterogeneity, I think that here in the audience there is a lot of people, not all for me, but a lot of people on infinite dimensional analysis and functional data. I think this is a very good tool. And for example, if you have a lot of information, records in time, but not in space, we can use some kind of model like this, but with infinite dimensional distributions in time and interaction in space. And also, if you have a lot of extensions, you can also use the opposite, independent on the information, spatial, like auto-regression, but with surfaces, with some interpolation. But I think that the heterogeneity in this framework can achieve, because you can consider a variable range of dependence which change with resolution in a space in one framework, or which change with increasing domain in time or local domain in time in another framework. So this is flexible, and you can mix also heterogeneity with some isotropic or homogeneity to facilitate also the summary of information through some orthogonal basic, like this type of periodic basis, which reflect the great influence of stations, because persistence depends on extensions, and also on the scale in space, also important. So thank you very much for your nice talk.
Can I just answer, say a word? Well, I still have this, I think. No, actually, what you said is wonderful, and it actually connects to another project that I'm working on, which is involving what's called reflectance. When you look at leaves, they have a certain reflectance. In fact, it becomes a bandwidth, and so it's natural to use functional data to work with that. And then we have leaves collected over spatial locations, so we have spatial functional data over bandwidth, and we've been doing exactly what you're suggesting, and you can do it with basis functions, you can do it with kernels, you can choose however you like to use the representations, but it's exactly what you suggested, and it works wonderfully, so I completely agree.
Great. Thank you so much. Thank you. And we have organizer has prepared a present for you for your nice talk, because you are here with us, so this is present for you. Thank you very much.
Thank you. Shall I take it out? Is it customary? Buena caja. Shall I open it? Okay. Momentico.